Hi folks, we're going to take a look at page 143, number 13. So here this is just a different way of forming a box, and in fact we're forming a closed box here. So these lines are where you're going to fold the box over. Okay, so this is going to be, so first of all let's realize that this here is going to be the base of the box that you're forming. Okay, so this is going to be the length and this is going to be the width of the box. And this little portion here, which is equal to x, is going to be the height of the box. So here we have x, here we have our length and width, okay? And then these portions here become the sides of the boxes, okay? So we are looking for, in A, we're looking for a function that expresses the volume of this box. So we know that we're looking for length times width times height. Okay, we already have that the height is just equal to this variable x. So we're hopefully going to be able to write the length and width with respect to the same variable x. And I would say that the width is pretty easy here because we see it's this whole part, okay, minus these little bits of value x on either side. So the width is just going to be 20 minus 2x, okay? The one that maybe requires a little more work is the length. Now I'm gonna get to this the long way, okay? But just to show you how you could figure it out if you're not seeing it intuitively. Okay, so let's take a look at this whole length here of the cardboard is 36. Okay, and what makes up this 36? Well, we see that we have two lengths. This one here, that one there. If this is the base of the box, this is going to be the top of the box. These have to have the same measure. So we have 2L, okay, plus these two little bits that are of length x. So this is 2L plus 2x. So if I want to solve for L, well, 2L is equal to 36 minus 2x, and then divide both sides by 2, and I have 18 minus x. Okay. You could have figured this out by other means, but this is the one that's the most direct, I would say. So our volume now is given by, now I can write these in any order, so I'm going to choose to write the height first. Since it's multiplication, I can give it any order. So I've got x, which is the height, times length, which is 18 minus x, and then I've got the width, which is 20 minus 2x. Okay, and so here we have a function which models the volume of the box depending on our choice of this value x. Okay, so let's move on to part B, and they want us to determine the possible dimensions of the box if the volume is to be 450. Okay, so now in B we're just taking this model that we found and we're just inputting for the volume 450. All right, now while this is in factored form, I don't have this equal to 0. So that means what I have to do is bring the 450 to the other side, rewrite it in standard form, and then from there, hopefully I can solve by factoring. Okay, so here we've got, let's start by multiplying this out. So 2 times 18 is 36, so times 10. So here we have 360. Here we have negative 36 minus 20. Negative 56x, and then here we have plus 2x squared. Okay, and of course we've got the minus 450. Okay, and lastly we've got, let's multiply all this out, and I'll also put it in order of degrees. So first we've got our 2x cubed, okay, then we've got our minus 56x squared, then we have plus 360x, and finally this minus 450. All right, so this is the equation that we have to solve in order to determine the dimensions of this box. And I look at the question, it says round answers to the nearest tenth of a centimeter, and that indicates to me that I'm probably not going to be able to factor this nicely, and in fact it doesn't. So what you would do is you would just graph this on Desmos or use a polynomial equation calculator. So stick it into the polynomial equation calculator and it'll give you your answers. Okay, so I graphed it here and I'm just going to kind of see if I can turn this around and show you my graph. Okay, and so you see that I'm looking for where this is equal to 0. So one of the zeros for x is 1.65. The second zero here is we'll just say 7.1. And the last one here is 19.3. All right, let's come back down. All right. So now we've got our three possible values for x, but you want to ask yourself, are they all reasonable values? All right, the 1.65 looks good. The 7.1, let's check that one, because remember, our length has to be 18 minus x. So 18 minus about 7 gives me a reasonable number, and 20 minus 2 times 7, which is about 20 minus 14, gives us a reasonable number. However, when I check the 19.3, I can see that this is not a reasonable possibility, since right away my length is going to be a negative number. So we have to eliminate that possibility. So I guess we've got two possible boxes. Box 1 would be 1.65 centimeters by, so now here let's take our calculator, and we've got 18 minus 1.65, so we've got 16.35 centimeters by, and the other one is 20 minus 2 times 1.65, which is going to be 16.7 centimeters. So that's box 1. And then box 2, the other possible dimensions I could have for this volume is we do the same thing now. So we've got 7.1 centimeters by, and 18 minus 7.1 is equal to 10.9 centimeters by, and 20 minus 2 times 7.1 is equal to 5.8 centimeters. Okay, so two possible boxes that achieve the same result. Obviously, this one here will have smaller height. Okay, this one is going to look a little more like a cube, okay, because the values are fairly close together, and this one here will be a much thinner box. So I guess you decide on which one to use depending on how you want to present your product, which I think in this case here was a box of chocolates. All right, so just to recap, so first of all, because we were looking for the volume of the box, it was about understanding what was going to represent the length, width, and height. From there, you write your model, and then once you have your model and you know your volume, we had to do some algebra before we can solve the problem, which in this case here had to be done using technology. Okay, that's it for this one.